What's up, brain developers? We are going to talk about our very first of Newton's laws. All right, first of all, do you see how this is a mouse and that's not a mouse? What the? How do I get it to be a mouse? There we go. All right. Now back. All right, perfect. Okay. So we're going to talk about Newton's laws today. Actually, not plural, just singular. Newton's law. Specifically his first law. It's gonna be tight. I love Newton's laws. They're super useful. In fact, for the rest of physics, all the way up until you are getting a doctorate, you're going to use Newton's laws for everything. These are the most ubiquitous things in physics. So we should probably learn them, right? So let's go ahead and dive into the first of Newton's three laws, the trilogy. So let me tell you what it says, and then let me tell you what it means, right? So Newton's first law says, an object in motion tends to stay in motion, and an object at rest tends to stay at rest unless acted on by an unbalanced force. Okay. So that's some stuff, right? I find this verbiage to be a teeny tiny bit misleading. So I think there's a better way that we can say this. What this means is that if the forces are balanced, that is, they cancel out, the object in question won't accelerate. So the reason I think this is misleading is because the word tends means like that's usually what happens. But this is a 100% kind of deal, right? This always happens 100% of the time. There's no tending, right? There's no tendency. This isn't like statistics, right? This isn't a maybe thing. This is a it's gonna happen. Disclaimer, these statements are not 100% true for quantum mechanics. So what Newton's law says is that if all the forces on an object cancel each other out, meaning there's a push to the right at 10 newtons, and there's a push to the left at 10 newtons, and there's a push down at 3 newtons, and there's a push up at 3 more newtons, and then there's a diagonal push this way at 4 newtons, and then another one here at 4 more newtons. As long as they all cancel each other out, then the object is going to keep on keeping on, as I like to say. It's gonna, if it's moving, it'll stay in motion, and if it's sitting there, it will stay sitting there. So forces can cancel. And if we add them all up and they equal 0, here's the important part. Acceleration equals 0. We can maybe even formalize this a little more. Let me introduce you to some Greek letters. Let's move this over here. If, and you've seen this in mathematics, the sum of the forces equals 0, then our acceleration equals 0. So this is the Greek letter sigma, not to be confused with ligma. And then this is a force. There are, of course, some things we need to talk about as far as this goes, but as long as all the forces equal 0, then the acceleration is 0. Likewise, this can go backwards. If we know that the acceleration is 0, meaning the object has a constant velocity, then we know for certain 100% that all the forces are equal to 0. Or rather, they sum up to 0. They don't have to be 0 individually, but collectively, they're 0. Okay. Cool. I think I've beat that horse to death. Let's talk about a little disclaimer about vectors really quick, because I'm gonna kind of hand wave a little bit, but I promise we will come back to it and I will teach you the full thing in a later episode. But for right now, I just don't want to overwhelm you with too much worrying about trigonometry and like the way stuff's pointing and stuff. So, disclaimer, vectors can be broken up into an x and y component, meaning if you have a force diagram and you've got something like this, this is, let's say, 14 newtons. Okay. You can split this thing up into two component vectors. It has an x component that is, that piece of the triangle. And then you also have a y component, right? So this thing is our force, okay? You can talk about how much of this force is in the x direction and how much of this force is in the y direction. You can calculate both of these things and separate a single force into an x force and a y force. That's allowed, and we're going to do that later. But for right now, because this is a triangle and we need to use Pythagorean's theorem and some trigonometry, we are not going to do that. We're too early, right? We're still learning Newton's laws. We're not ready to do component vectors and stuff yet. This will come back later, though. Okay, and disclaimer. Void where prohibited. You must be 18 or older to play. Please ask your parents before going online. All right, so let's talk about some examples first. So what are some examples of when the first law would apply? So the question we need to ask ourselves is velocity constant? There's two components to that. Speed, of course. Is it going the same speed the whole time? And direction. Does it turn? Does it go up and then down? Is it curving? If any of that's true, not constant, right? It has to go the same speed in a straight line for velocity to be constant. So, a block sitting at rest on a table. Okay, so 1 second, it's sitting there on the table. A second later, it's sitting there on the table. 3 seconds later, it's sitting there on the table. The velocity is constant. It is constantly 0. And then direction doesn't really have a meaning when something's 0. So we would say, yeah, of course. This is definitely a case where the first law would apply, and we'd want to somehow utilize that to solve a problem, maybe. A ball rotating in a circle on a string. So you've got like your table here, right? And then you like put a thumbtack down, and then there's like a ball, and it's doing one of these numbers, right, in a circle. This would not be Newton's first law because it's going in a circle. That means the direction is changing. 1 second, it's going that way. When it's here, it's going that way. When it's there, it's going that way. So the direction is constantly changing. This is not a good scenario for Newton's first law. It does not apply here. Okay. A hot air balloon gently ascending. Does ascending actually have two C's here? Ascending? That might be a typo. At a constant speed straight up. These are the two important phrases. Constant speed, yep. Straight, yep. So this would be a case where all the forces are balanced and Newton's first law applies, even though there's a hot air balloon rising up into the air. I think this is one of those weird examples because people feel like something floating up, it's flying away, literally. The forces can't be balanced, it's flying. What's with gravity? Well, gravity is being canceled out by another force. So it is balanced, and that's what keeps it from flying away. Okay. A car driving at a constant speed on a straight road. Okay, perfect. Constant speed, check mark. Straight, that means it's going in a line. Yep. this one would be an example of Newton's first law, and all the forces would have to be balanced. Lastly, we have a dog on its leash pulling with all of its might while its owner firmly holds the leash, preventing the dog from going anywhere. Okay, this one's a little ambiguous, right? But I think the important thing here is preventing the dog from going anywhere. So you've got this dude or dudette. It could be a dudette here. It's a dude with long hair. We'll compromise. And then holding the leash. And then what do dogs look like? It's a stick dog. Looks like a little potato. Right? And then this dog is hella ticked because it's trying to leave. But because this dog is here and it's not moving anywhere, it's stationary, its velocity is 0. Constant velocity, end of story. Newton's first law applies. The forces on the dog are balanced. All right, glad we talked about those. So there's some examples. Let's go look at some like real problems, and then we're gonna learn how to do a sum of forces, which is the really key important thing here that's gonna come up over and over and over and over and over for the rest of your life, right? Someday you're gonna be sitting at McDonald's, you're gonna be flipping burgers, you're gonna say, why didn't I go to college? Why didn't I stay with Thomas? He was the best thing that ever happened to me. He was so handsome. If I was with him, I'd be sitting in Cancun right now. Just kidding. I digress. Sorry. But forces are going to reappear for the rest of your life. So you're going to, and when I say the rest of your life, I mean like the next 2 months. But let's talk about how we should approach a force problem. So first of all, we're going to want to draw a force diagram. We talked about that in the last video. Check mark, you're masters of that. We're going to want to write a sum of forces equation. I'm about to teach you how to do this, so don't trip out, you'll learn. Once we have written the sum of forces equation, these are the only 2 physics steps in this process. These last 2 are physics wonderful. What is this? This is supposed to be a bracket, but oh well, now it's a thing. This is math here. So we're going to do 50% physics, 50% math, because we're not haters and we can swing both ways. You feel me? So let's go ahead and apply these 4 steps. Okay. Let's go look at an easy problem first. This is what I fondly call all reliable, because this is the situation, right? You can't present this situation to someone and have them be like, I've never seen anything like that before. You've never seen something sit on a table, bro? So we've got a 5 kilogram mass sitting on a table at rest. At rest, you say, velocity equals 0. Later, still 0. So acceleration is 0. First law. So we're going to use Newton's first law here. Okay, let's start with step 1, draw a force diagram. Let's draw a picture first, just because, you know, you want me to not draw a picture? What do boxes look like? Something like that, okay. There you go. Sit on a table. We're going to draw a force diagram for the box. It doesn't really say something about the box, but it says find the normal force that the table applies to the mass. So the thing we're interested in are the forces on the mass. So we should look at the force diagram of the mass. And you're going to say, what are my other options? Well, we could have looked at the table. That's definitely something we could have done. But you're supposed to do the mass, because if you don't, it doesn't work. And you can tell kind of because we're looking for a force that's being applied to this thing. So we want to look at this thing. So condense it down to a point. Of course, we have weight. That's the easy one. Weight down. Okay. We do need to remember something about weight from our last video. Weight is equal to the mass of an object times the acceleration due to gravity. All right. So we've got our weight down from our mass. What is counteracting this? Why doesn't the mass fall? Why is it sitting stationary at this position in space? It's because there's this big solid table underneath. So the solid table touches the solid box and pushes up on it. So that solid contact force, we call that the normal force. Again, normal simply means perpendicular here. So we know, and not just because we feel it now, but because we understand Newton's first law, that these must be equal. Because the acceleration is 0, all the forces must cancel one another out so that they equal 0. So now we can say with certainty that these are equal for a reason instead of just because it feels right. So here's our force diagram. Let me move some of this stuff over so I've got some more room to do the math half of the problem. Okay, so now we need to write a sum of forces equation. But before that, let's just define a few things. I want up to be the positive direction. End of story. You should probably say what x direction is positive too, but because we're only looking at the up-down stuff right now, it really doesn't matter. So we're not gonna. All right. So we're going to write our sum of forces equations, your very first one. I'm so excited for you. All right. The sum of forces is equal to, well, we know it equals 0. But how do I write this? What is this part? Because this is the part we need. What you do is you just add, because that's what this thing means. This means sum, and sum, S-U-M, is the math word for add. Add the forces together. So what are our forces? We have the normal force, and we have the force of gravity, or weight. Now here's the important physics part. We have to add or subtract them depending on what direction they are. So we decide direction based on how we say we're assigning direction. We said up is positive. So the normal force points up, it's positive. Weight is down, so it's in the negative direction. So in our sum of forces equation, we make weight negative because it's in the negative direction. So now we are all set. We are trying to find the normal force. So let's solve for it. We just add weight to the other side. So the normal force equals weight. Okay. Now we're going to plug in some stuff we know. We know that weight equals mass times gravity. So let's substitute that in. All right. Do we know a mass? Yeah. Mass is 5 kilograms. Mass should always be in kilograms because newtons, remember, are kilograms meters per second squared. So we need the kilogram mass for it to be in newtons. Okay. So we're going to plug in the 5. G is 10. And now you should be screaming at me. Mr. Barton, you said G equals negative 10 because down is the negative direction. I understand. But we've already taken care of that direction with this negative sign up here. So when we plug in G, we're going to plug in 10, understanding that we've already taken care of the negative direction with that negative sign. So now we just care about numbers. So N equals 5 times 10. Our normal force equals 50 newtons. And it's up, so it should be positive. And there you go. We did our first physics problem with sum of forces. How exciting. All right. Are you ready for a harder one? Okay. I won't explain so much on the next one. We'll just breeze through it. Sometimes I feel like I teach a little slow for you guys, but then other times I think back to previous students who kind of cried a little bit and, you know. All right. Let's look at a slightly harder problem, and then let's talk about why this is titled this. So it says, There are two blocks stacked on top of each other. Okay, I can do that. There we go. Sitting on a scale. Okay, I can do that too. There we go. All right. That's measuring in newtons. There we go. Cool. That's a scale, not a skateboard. The top block is 1 kilogram. The bottom block is 3 kilograms. What is the normal force that the scale is applying to the bottom block? Okay, so we're asking about something being applied to the bottom block. Let's go ahead and look at both blocks. We are really interested in this block. And if you were a little more experienced with force diagrams and such, then I'd say let's just look at the bottom block. But we need to look at the whole system to get a good understanding because we're still learning. So let's start with the top block. Okay, I'll do it in a nice teal color. So this top block, of course, has weight. We'll call it weight 1 for the 1 kilogram block. And then it's sitting on this solid 3 kilogram block. So there is a normal force up. And we'll call this normal force. Let's talk about how I'm going to label this real quick. There's this thing called feeler dealer notation. And this is like physics teacher speak. This is not PhD physicist speak. When you write subscripts, some physics teachers like to use the feeler dealer notation, meaning you write the label of the thing feeling the force first, followed by the label of the thing dealing the force after. So this is normal force of block 1 dealt by block 3. So some people would label this normal force 1-3, doing feeler dealer notation. This will be a very important idea for the third law, but that's preview. For now, what I'm going to do is call this normal force T for top block, because I think that makes more sense to me. Okay. There we go. There's our force diagram. Okay. Let's look at the bottom block now. Pink. Of course, we have weight. This thing is 3 times as big, so its weight should be 3 times as long. That's probably not 3, but it should be. Okay, so weight 3. Now, we have the normal force from the scale. I'm going to put normal force B for bottom block. And we have this block sitting on top. Is this block going to push what direction on the bottom one? What do you think? Well, the force is on the top of the block, but this block is, of course, pushing down on that block, right? It's trying to squish it. So the normal forces go both ways. If I push up on that block, it pushes back down on me, right? You feel how heavy this block is. So the contact force from this block on the bottom block is pushing down on it. So I'm going to put that down there. Okay. There's a roundabout way. Actually, it's another law. I may have spoiled something for you later. The third law says that this little normal force down is whatever this is, which just happens to be equal to the weight. So this is the normal force from the top block pushing down on the bottom block, and its length is equal to whatever the weight of the top block is. I'm paraphrasing a bit, but trust me on this. Okay, so these are equal. We cannot mark anything equal here because this bottom block is stationary. All its forces are balanced through the first law. But I can't say this is equal to this because it doesn't equal this force alone. It equals this force plus this force. So this normal force is holding up the weight of both blocks. So that's kind of the trick to it. So let's go ahead and try and write our sum of forces for this situation. All right. Sum of forces. We have, let's say up is positive again. Our normal force from the bottom block, or on the bottom block by the scale, is pointing up, so it's positive, minus the weight of the top block, minus, ooh, I'm running out of room. We got to scoot more stuff over. The weight of the bottom block equals 0 because of Newton's first law. It's stationary, it's not accelerating. Okay. Now we're going to go ahead and solve for the thing we're interested in, the normal force. So we're just going to add weight 3 over and add weight 1 over. So N, or normal force on the bottom block, equals, when I add these over, they become positive, weight 1 plus weight 3. Now we substitute in equations for our weights. So let's do white. Weight 1 is the mass. It's mg. It's the mass of the 1 kilogram block. It's 1 kilogram times g, which is 10, plus the mass of the 3 kilogram block. It's 3, plus g is 10. Remember, the g's are just positive 10 because we've already taken care of down with these negative signs here, equals n on the bottom block, normal force on the bottom block. So 1 times 10 is 10, 3 times 10 is 30, 10 plus 30 is 40 newtons. So the normal force, the scale, is exerting onto this bottom block. The force up from the scale is 40 newtons. Let's go ahead and talk about the title of this problem. Scales are force gauges. So scales don't actually tell you the mass of things. What they do is they measure this normal force, do a little bit of math in their little scale brains, and then they say, if there's this much normal force by me up, then this much weight must be sitting on top of me. And then they spit out the weight, right? Pounds, lbs, or rather pounds, right? I guess I could just spell it out. Like the imperial unit of weight. The thing that you hide from your boyfriend and girlfriend because you've been eating too many Takis. Pounds is the like foot version of newtons, right? It's the ugly American unit of force. We will never use pounds. I don't even know how to convert newtons to pounds. That's how often we're not going to use it. So pounds is not necessarily only for weight. It's actually a force measurement. So your scale is telling you what the force of gravity is on you. And if you think about it, if you take your scale to the moon and you stood on it, it would say a smaller number than if you're on Earth because you weigh less on the moon, because G is a smaller number. Yeah. So these aren't telling you masses. They're not telling you how much of you there is. They're telling you how hard the Earth pulls on you. So, fun fact, when the moon is directly overhead, scales tell you weigh less. So if you ever want to feel good about yourself and lose like an ounce, make sure you step on the scale when the moon's over your head because you'll weigh less. Also, if you weigh yourself on top of a mountain, because you're farther from the center of the Earth, you'll also weigh less. So you should be on a mountain with the moon over your head, and then you'll weigh the minimum amount you could. So fun trick if you're ever on top of Mount Everest. All right. I think I have, is it just that one more? So last one, we're still going to keep it nice and simple, but let's look at some stuff in the X direction just so we can kind of see some other stuff. This one is brain dead easy too, though. So You and a friend are trying to move your table saw, please don't hurt yourselves, from one side of your garage to the other side. You stand behind the table saw and push with a force of 500 newtons. Your friend is on the other side and is pulling with 300 newtons. The table saw doesn't budge. How strong is the force of friction between the table saw and the floor? So let's draw a quick little picture. What do table saws look like? Something like that. Is that a table saw? Yeah, okay. So you're over here. And you're going to push on this thing. And then your friend is going to put their hands on that. And then they're going to pull with all their might. Wait, not X's. We don't want X's. We want exertion I's. There we go. Okay. So we're trying to move this thing, we'll say to the right, and we'll say to the right is the positive direction. All right. Let's go ahead and do a force diagram for our table saw, because that's the thing where all the forces are acting on. So that's the thing we're interested in. So for our table saw, we have weight down. Of course, we have the normal force up. We have force applied by me. So I'm going to just put force M for me. Then we have a slightly smaller force applied by my friend. And then friction is keeping us from moving this. So in the y direction, we can see normal force and weight are equal and they cancel each other out. In the x direction, we've got two forces to the right. So friction needs to be to the left. Lowercase f for friction. And it's going to equal these two forces here to cancel them out and equal 0. So because the thing we're interested in is moving left and right, we're trying to slide this thing horizontally, and we're looking for friction, which is in the x direction. We don't really care about this y direction. Ignore it. We're going to write a sum of forces in the x direction. And I pull a little subscript x there. You can probably imagine what we're going to do when we have two directions. But so let's write our sum of forces for just the x direction for this problem. We have force of me. I'm going to keep it positive because I said to the right is positive. Plus, because also to the right, the force of my friend. Minus the force of friction, because it's to the left, equals 0. Cool. So now we're going to solve for friction. I could move these both over there, but it's probably easier to just add friction over. That'll still isolate it, right? Let's do math intelligently. So we have the force from me plus the force from my friend equals the force of friction. So this is going to be 500 plus 300 equals F. So lowercase friction equals 800 newtons. And then now at the end of the problem, to indicate that the force is in what I have said is the negative direction, I go ahead and just slap a negative on that thing. When you are doing these problems and you're including directions here, everything's going to come out positive every single time. So at the end of the problem, you kind of have to step back, evaluate, okay, should this be positive? Should this be negative? What way did I say is positive? So our force of friction would be negative 800 newtons. And then this negative isn't saying we're like negative pushing on it. That's not a thing. It's saying that we're pushing in the negative direction. So just like velocities, accelerations, displacements, just like the sign for them is directional, sign for forces also indicates direction. All right, so there's your notes. I'm going to have a couple of problems for you to do. You're going to go ahead and try to write some sum of forces equations, maybe solve for a couple of things. It'll be a great time. You'll see. Until next time, have a wonderful day, ladies and gentlemen.